ADC, right? And so you can make these measurements, on the same person at multiple time points. And so it's exactly the kind of nice data that you can use to drive a math model, which I promise we will get to. As opposed over here to a non-responder where there's basically no change in the diffusion. You can look at the properties here, they're very similar. And so if you do the ROC analysis on the diffusion stuff, then you can get an area under the curve of about 0.81 for predicting who's going to respond and who's not going to respond after one cycle of therapy. All right, so what we're going for now is we're trying to get patient-specific data that we can use to calibrate our mathematical models. So far, we've talked about anatomical stuff, either mostly just through MRI, we'll do CT here in a moment, that can furnish our computational domain. It lets us segment the tissue, it lets us register images across time. And then we have to worry about these functional characteristics to assign model parameters to let us predict how things are going to go forward in time. How are we doing out there? Any comments or questions or anything so far?
Mm-hmm.
How's everybody level of misery? 7 being perfectly miserable, 1 being best day ever. How are we feeling out there?
Very exciting.
Very excited. Excellent. All right, that's all I needed. Very good. All right, so this is our diffusion stuff. Another one is contrast enhanced MRI. This is where we get a series of images before and after we inject a contrast agent. And so if you stare right here, that there's this invasive ductal carcinoma right here, and as this cycles back around, as the contrast agent is ejected, boom, right there, you see it enhances. You also get this blush from the fibroglandular tissue, but you don't get it from the adipose tissue because, of course, adipose tissue is storage. It's not vascularized, so there's not going to be any contrast agent out there. But you can picture in your mind's eye, each pixel is going to get its own signal intensity time course, which you can then analyze with the pharmacokinetic model to tell you about blood flow, vessel permeability, tissue volume fractions, these kinds of things. And so, people do this as well. So here, these images are now ancient. They're over a decade old, but they deliver the point. Also, I actually took these images. This was back when I was actually running experiments and studies, so they hold a place in my heart. But anyway, definitely the quality of the images have improved over the last decade. But anyway, the point here is that each pixel here has a red, yellow, green, or blue thing, and the red indicates higher perfusion permeability, blue indicates lower. So you can see from pre-therapy to post-1 cycle, the person who responds has a big reduction in the number of vessels that are perfusing, that are delivering nutrients to this tumor, right? So that's a positive sign. As opposed to a non-responder, in this case, if anything, there's been an increase in the number of red voxels indicating increased perfusion permeability. So this is unfortunately a non-responder. So you can do the ROC analysis of the two, and you get a 0.77, which is not quite as good as the diffusion on the previous slide. Later, we'll talk about combining these two things, and you do quite well. So now, this contrast enhanced MRI stuff and this diffusion stuff is now actually part of a standard workup in many, if not most places for breast cancer, and it's certainly part of if you're familiar with the iSpy trial that's been going on, now they're up to iSpy 2.2. It's been going on in breast cancer for good grief, maybe 12 years now. Now they're using these techniques. So they are now commonplace things that you can use to drive a math model. If we move on to x-rays here, we're kind of moving up the electromagnetic.
Can I ask a question? Sorry, from the last slide, there was, when you say ROC analysis and that it's like 0.77, what exactly do you mean by that?
Oh, I'm sorry. Yeah. So this is the area under the ROC curve, and so this is a whole branch of how to. Okay, let me back up. This actually grew up in the 1940s and 50s. It initially came up in trying to understand radar images. Whenever you're charged with trying to make a binary decision, a yes/no, a yes/no decision here, benign or malignant, or responder or non-responder, ROC analysis comes to play. And so you have some biomarker, in this case, this perfusion permeability, and you look at distributions of it of patients who are responding or not, and you try to find the cut point in the distribution of parameter values, and you say everybody to the left is a responder and everybody to the right is a non-responder, or vice versa, or whatever. And then you want to assess how good that cut point is. And so an area under the receiver operator curve of 1 indicates a perfect diagnostic. You've landed on something that is absolutely perfect. An AUC of 0.5 is a coin flip, and in between is in between. So in speaking loosely, this has a accuracy of 0.77 for being able to separate a responder from non-responder using this biomarker of perfusion after one cycle of therapy. Is that okay?
Yeah. Okay. Thank you.
Yeah, you bet. Yeah. It's probably it's worth looking up. In a one page description on some website, you'll have it, no problem. And it's a good thing to have in your back pocket for analyzing no-go decisions. Yes/no decisions. All right, then we move on to X-ray. This is the very first X-ray that was ever taken of the human body. This is Mrs. Röntgen's hand. Wilhelm Conrad Röntgen was the discoverer of X-rays. This is her wedding band right here, and this took 15 minutes to make. And she, like a lot of people who are working with radiation in the early days, ended up succumbing to that. So nowadays, this is used for breast cancer screening, and it's the image itself is less than a fraction of a second, although the positioning and the rest of it is, I'm told, a bit miserable. But this is what an X-ray looks like for a healthy breast. A fibroglandular tissue is the whiter stuff. The adipose tissue is the grayer stuff. And then this is a benign cyst. This is a textbook example. It's well circumscribed. There's no invaginations into the surrounding tissue. So this is nothing to be concerned about. And then this is a malignancy. You can see that it's not well circumscribed. It's invading into the surrounding tissue. So this is going to get follow-up. This is what was probably discovered on screening mammography. So the next one is diagnostic mammography with ultrasound and or MRI. But X-ray radiography has this fundamental limitation. It takes a three-dimensional object and smashes it into two. So that third dimension is all smashed in. And when you look at your two-dimensional image, every pixel in there is basically just the sum total of all the attenuation along that third dimension right there. So we got to get past that. So CT, computed tomography, X-ray computed tomography allows for true 3D image acquisition. So what it does is it acquires a series of projections from many angles around the subject, and then each set of projection is reconstructed filtered via something called filtered back projection. It's a really cool mathematics behind it. It won the 1972 Nobel Prize in Medicine and Physiology, and it has good spatial resolution. So here's a cross-section. This is a healthy woman right here, a heart, lungs, nothing going on here, vertebral column. This is the breast tissue up here. And then this is, of course, someone with a lung tumor that's growing right here. And so you can imagine how this is a big leap forward in a quantitative characterization of each patient, because if we just had that X-ray radiograph and it was projecting in this direction, or even this direction, it doesn't matter. If it was one projection, what you'd get is one image down here that was the sum total of all the attenuation along this line right here. So it might be very difficult to see this lesion if it's summed with everything along this line right here, which is what you'd have in a 2D projection. But these 3D slices, this that eliminates all that ambiguity and is clearly worthy of a Nobel Prize. This was a huge leap forward in medicine there at the beginning of the 70s. So the next thing along the line is PET, positron emission tomography. We use a lot in the clinic. They use a lot of FDG PET, fluorodeoxyglucose. So there's these radioactive elements that can be incorporated into metabolically relevant compounds, and that's exactly what they do here. Fluorodeoxyglucose. You take a glucose, you kick out the oxygen, you put in 18F, which is going to emit positrons, and that's what's going to lead to your image. So for PET, we use positron emitters. These are radionuclides that have don't have a good balance of neutrons to protons in their nucleus, and so the proton will be swapped out, or not swapped out. It will decay and give off a positron and an anti-electron and an anti-neutrino, but that doesn't matter for us. We can't detect them anyway. So the positron is emitted. It goes and finds an electron, and they annihilate, and you get two photons going in about 180 degrees opposite to each other, and they're then detected on a ring of detectors, right? So you inject this radionuclide, it accumulates wherever it does. And this picture, this is a healthy person, so the heart, of course, is very metabolically active. The kidneys are filtering it out, sending it to the bladder. This person might have been doing a lot of talking right before this. This is the trachea that lit up. And then if you squint, you can see the brain just kicking in. And of course, the brain is your biggest user of glucose, and so it is metabolically very hot, which actually limits the utility of FDG PET for looking at brain tumors because the background is so high. Right, so when the positron is emitted from the radionuclide and it goes and finds an electron, goes and finds, what's going on? Goes and finds an electron. They are antiparticles, and so they annihilate, and you get two photons traveling in opposite directions where they're measured by this detector ring. And so once the detector grabs them, it's known that that event took place along the line that connects the two detectors. And of course, you get tens of millions of these events, and you can use these things to then reconstruct the image. So what's actually happening to get this? This is the compartmental model that people tend to draw, right? You have your fluorodeoxyglucose. There is your F18 that's been put in place for oxygen right there. That's going to be pulled into the intracellular space. There's this enzyme hexokinase that phosphorylates FDG in the sixth position here. Where are we? The sixth position up here. So that means you now have what's FDG 6 phosphate right here. And this is the point where the cell recognizes that this is not glucose, that it is something different than glucose. This is what glucose happens, and then it continues along the metabolic pathway. But here, the body recognizes that this is, at this point, that it is not glucose, it's FDG. And so what happens is the FDG just stays there inside the cell, happily emitting its positrons, which then find electrons, which annihilate to give those detectors off, to give those photons off that you then capture with your ring of detectors. And so wherever this stuff accumulates is where you'll get counts, and that's how you reconstruct the image. So this is a healthy person. And then here is this is longitudinal imaging of FDG PET with locally advanced breast cancer. So here is a patient that had disease, non-pathological complete response. This is a baseline after one cycle, after all cycles. You can see that the change in SUV, in FDG has not changed very much over time. As opposed to a responder, there's been a dramatic reduction right here. And so this patient went on to be a complete responder, and this one did not. Okay. And then here are someone a few years ago did a meta-analysis of FDG PET and found that the accuracy for predicting the response of breast tumors to neoadjuvant therapy had this sensitivity and specificity of 82% and 79%. So that's pretty good. One more thing I think here for PET. This is receptor targeted PET. So let's review. So far we've had anatomical MRI and anatomical CT that we can do things to like register the images over time, set our computational domain, segment the tissue into healthy tissue in the tumor and so forth. Then we moved on to diffusion MRI to tell us about cell density, cellularity. We contrast enhanced MRI to tell us about blood flow and permeability, vessel permeability and tissue volume fractions. Then we looked at FDG PET to tell us about glucose metabolism. And then you can also do receptor targeting with PET here. And so this is, again, just trying to keep this in one disease setting. This is in breast cancer. I'm looking at estrogen receptor positive breast cancer. There's this tracer called fluoroestradiol, and it is targeted to the ER receptor on breast cancer cells. And so it will, or wherever there are estrogen receptors, which is a problem for background in some places, like here in the gut. But you can see that these breast tumors here are lighting up, and so they must be ER positive. Also, FDG is being lit up, so they are metabolically active. And in a different patient here, there's no lighting up in the breast region right here, but there is this background here, which makes it a problem because there's lots of estrogen receptor positive cells in the gut. But you also see this tumor right here that's FDG avid. So this is a metabolically active tumor, but it is not ER positive. So you would then know not to give, for example, an aromatase inhibitor or anything that's going to hit the estrogen receptor. So patients with low FES uptake are unlikely to respond to endocrine therapy. And now it's kind of old news, about 5 years old, that FES can help solve most clinical dilemmas that may remain after the standard workup for ER positive versus ER negative breast cancer. So this is an example of targeted PET attacking that. Then the very last imaging thing we'll talk about before we then move into mathematical models, and we'll pause after this slide to see if there's any more questions. So please get those going if something's eating at you. So most common immune checkpoint inhibitors, ICIs as they're called, are monoclonal antibodies that bind to one of these three guys right here. So if you could figure out which tumors are overexpressing these guys before you start the immunotherapy, this would be a big leap forward. This isn't an area where therapy is far ahead of what we can do imaging-wise, because when immunotherapy, as you guys know, when immunotherapy works, it is magic. but it doesn't work for everybody, and we don't know a priori who it's going to work for, and when it doesn't work, there could be significant side effects. So figuring out if a patient would benefit from a particular immunotherapy is a huge issue right now in oncology, right? So what they do is these large molecules, these MABs, these monoclonal antibodies, are readily labeled with positron-emitting isotopes. And the idea is that if you have one of these antibodies that are labeled with the labeled isotope, it's going to work similarly to what FDG does, except for FDG is pulled into the cell. These guys are designed to hit cell surface receptors that are upregulated in certain kinds of tumors. So when it comes to diagnosis, you could use a PET tracer to select the proper one to see if the target you're going after, namely perhaps one of these three guys, is present, and then that would guide treatment, and then you could then do different types of things to assess for response, and you then loop back through this. But here, the big thing that people, the first step in this pathway is to figure out what the receptor activity is throughout the entire tumor to see if you're really getting immune infiltration and being able to, which would make the patients a candidate for an immunotherapy. So now there are PET tracers for CD8, PD1, PD-L1. They're in very early human studies, right? This is a new thing. So we're going to take a quick look at one right here. Most of them are labeled with 89 zirconium, which has a really long half-life because it takes a while to accumulate. So you can't have something with a shorter half-life like FDG, which has a half-life of, oh, good grief, I should know this. It's like 110 minutes, so just around 2 hours, I think. So after, say, 5 or 6 half-lives, most of it has been removed from the system. And the half-life of 89 zirconium, I should also know this, but it's on the order of days. I don't quite remember how long it is, but it is on the order of days. So here's day one, you inject, and you can see it's in the vascular system right here. But then as you get along days and days here by day 6, it's pretty much removed from the vascular system, and it has been accumulated right here in this metastatic disease site. So this is a candidate, this is a patient that is definitely PD-L1 positive, and you would then make the guess that since it's PD-L1 positive throughout the tumor, that they would be a candidate for for an immunotherapy that is targeted for PD-L1.
Tom, yeah, let me just...
Over 6 days, the images show accumulation of the...
Tom.
Yeah.
Yeah,
Yes,
your video is breaking up a little bit, so maybe you want to stop your individual video, and that should be better.
Okay, I can do that.
Okay.
All right. I'm checking now. Can you guys hear me okay?
Yeah, I think this is better.
This is better. Also, this is better because then you don't have to look at me, which I understand can be a real problem for many people. So there's that. All right. So just to make sure that we're all on the same page for this is our last bit of imaging stuff, and this is kind of right at the forefront of where the field is. It's trying to build imaging techniques that can report on immune receptor expression so that the proper therapy can be selected. And so this is a leading candidate. The 89 zirconium radionuclides are incorporated into different kinds of monoclonal antibodies to see whether or not a particular cell surface receptor is expressed. And it's key that it has to be one of these crazier radionuclides because they have to have a long half-life because it takes a while to accumulate and the target of interest right here in this case. You can see that after 1 day, there's virtually nothing. There's a light enhancement after day 2, but after day 6, it's really lit up here in this metastatic site right here. So you would know throughout this tumor that it is positive for PD-L1, and so that would be the target to go after there.
Mm-hmm.
Okay, so that was all the imaging stuff. And again, just to make sure we're all on the same page, we talked about anatomical imaging through MR and CT. That sets our playing field, our computational domain, if you will. It lets us segment tissues. It lets us register images over time, which we'll need to do to calibrate images that I'll talk about in a moment. Then we talked about more functional characteristics with the diffusion MRI to tell us about cell density, and then the contrast-enhanced MRI to tell us about blood flow and tissue volume fractions. Then we moved to FDG PET to tell us about metabolism, and we talked some about different targeted tracer to tell us about different cell surface receptors. There was one for estrogen receptor positive, and there was another one that we looked at for PD-L1 positive. Now, so that was a ton of material, 20 some odd slides. So I'm going to take one slide each just to remind us of 2 cases that we're then going to use for a deep dive into the physics and biology-based modeling. So I hope I hope you're tracking with me and finding this. There's many ways to navigate this, right? I could have done high level stuff on all of this, so I tried to do a high level stuff on the different types of patient specific imaging data. We're going to narrow in on a couple of them and show how 2 of them can be used to populate models, and then I'll give examples of other ones so that we won't dive into as much. So to give you the sense of how to use patient specific data, patient specific imaging data to drive these mathematical models. So are you guys still tracking with me? Can I get a thumbs up or something indicating something? Okay, I see. Thank you, Amy. All right, very good. All right, wonderful. Okay, so here we go. Right, so again, this is just a reminder. This is not new material. This is our contrast-enhanced MRI. We're looking at the tumor right here. Contrast agent comes in, it lights up. In your mind's eye, a pixel, and contrast agent comes in, it washes out. We can analyze that with the pharmacokinetic model that tells us about how it's distributing and being delivered. And this gives us these maps. This is a perfusion permeability map. Responder has a nice reduction. And the number of red and yellow pixels indicate a reduction in blood flow, as opposed to over here, where if anything, there's been an increase, and it had a pretty good predictive value on its own. The other one that we want to remind ourselves about is the diffusion weighted MRI. Each pixel has a bunch of cells in it, and water diffusion is restricted because it's going to hit these barriers, these cellular membranes. And so you might have a reduction in the apparent diffusion coefficient here. If you give a cytotoxic therapy that's effective, as you move from here to here in time, less cells over here, less water restriction, and so your ADC distribution will shift to these higher values, and that's what we saw over here in this responder. Some initial distribution of low ADCs, and now there's a lot more red guys over here, indicating the cell density has reduced, right, as opposed to a non-responder. And on their own, the area in the curve is 0.81 here for these 2 things. So when we combine them into one thing, where's my final thing? Yeah, so this is just you can do this in the same patient. That's the only point here, is you can do these scans in the same setting at the same time within the same, the set of scans, soup to nuts for breast MRI is about 25 minutes. So you can get all these measurements in here. And then when you combine them, you're getting an area in the curve of about 0.88 for separating responders from non-responders after the first cycle of therapy. In a sort of retrospective population-based thing, you can separate responders from non-responders to the point that now these things are being used to assess response in prospective clinical trials to try to guide patients to one arm or another based on these measurements. That's being done in the I-SPY trials, which is a very large multi-center trial in the United States. But the key about it is that just on their own, since they have statistical importance, it gives us motivation for using these parameters as inputs into a mathematical model, all right? And so now we're finally getting to the part that you probably care about, but I felt like I had to at least, and I hope I didn't insult anybody's intelligence and you already knew all that imaging stuff, but those are some patient-specific things that we can get in the routine clinical standard of care setting, and now we're going to try to take those measurements and incorporate them into a math model.
Tom, I have a question, if that's
Yes.
all right.
Of course,
so you say that this method is being tested and it's after the first cycle of therapy. Do they go on to test subsequent cycles of therapy to catch, I guess, ones that are not caught in the first round?
Yeah, so this is a great question, and it depends on where you're getting your care. So in the standard of care setting at your private non-academic medical center, you will get this kind of scan probably some point at the midpoint of your therapy. When you're within the confines of a clinical trial, in particular the I-SPY clinical trial, I forget the acronym for I-SPY. It's some force acronyms where the letters are picked from the middle of the word, so it's a bit of a hodgepodge. But in those patients, what they're actually doing is they're doing an adaptive clinical trial where there's as many as 10 different treatment arms. So patients come in, and based on their biomarkers or cell receptor status, they go on one of these 10 arms, and then they have MRI before they start, and then maybe after a cycle or 2 of therapy. And based on that response, they'll either stay on that arm or they'll shift them to another one. And then actually in I-SPY 2.2, the one that's just coming online now, they get up to 8 scans during the course of their entire regimen based on how they're doing and how they're shifted from arm to arm. So if you're in a academic research-oriented medical center and participating in a clinical trial, it's more likely that you're going to be getting these scans more frequently. If you're in the standard of care setting, more likely than not, you might have one at at baseline when they're doing trying to do diagnosis. Then you'll definitely have one before you go to surgery. If it's for locally advanced breast cancer, you have the systemic therapy, and then you go to surgery. So there'll be one there for a surgical plan, and there might be one in the middle. Yeah. Is that okay?
Yes, thank you, Tom.
Cool. Yeah, great. Right. Any other thoughts or comments or cries of joy or shouts of misery? All the same to the torture. I guess you can't see me smiling anymore. So just sort of weird. All right. Right. So these parameters on their own are, at least in a statistical sense, able to separate responders from non-responders. Of course, I've only told you about, really one example in this locally advanced breast cancer, but it's used in lots and lots of different disease settings. But hopefully you're convinced that they're useful, and so now we can use them to drive a model. So our metaphor that we started, 10 years about this, and if you get nothing else out of this, I'd encourage you to kind of look this one up, because I think it's a nice, if I toot my own horn, I think it's a nice display of where we need to go in oncology. So just as satellites provide the data for weather forecasting, quantitative imaging data can provide the data for tumor forecasting. So you might have, in this case, this is a global map of humidity that's going to go along with temperature gradients and wind gradients. Pressure gradients are going to go into some version of the Navier-Stokes equations to give you a weather model to then to make a prediction of how the weather is going to proceed for some particular area in the next few days. So we don't have satellites, of course, but we have all these medical imaging data that we just talked about. So you might have a map, in this case, of blood flow versus cell density. That's going to go into a tumor model to make a tumor forecast. So that's our metaphor that we're going for the rest of today, right? So now we're going to dive into physics and biology-based mathematical modeling, and then we'll link it. We're going to dive into this. We'll have one quick example of how to link it, and then we'll dive into more detail about how to link it. All right, so if you open up section 1.1 of any mathematical biology textbook, you're going to see this equation, which you've probably seen a gazillion times. Of course, it's exponential growth. I got it on here just to so we can start from zero. So K is the proliferation rate, N is the number of tumor cells at some time T. So the rate of change of N with respect to time is directly proportional to the number of tumor cells N that you have there. And of course, you separate the variables and you get this exponential growth. So this is actually where you actually see this. If you put cells in a petri dish at early time points, they will grow exponentially. Even if you put tumor cells on the hymen of a mouse, they will grow exponentially at early time points. But they're going to start to reach their limit of what the system can support. And at the petri dish, there's a limit to how many nutrients you got there, and also there is the wall of the petri dish, and so you're going to grow up to the carrying capacity, right? So here's theta right here. This is the carrying capacity. As n gets close to theta, this number gets close to 1. So 1 minus the number close to 1 is close to 0, and the rate of change gets close to 0, and that's what this leveling off is. We know this, right? Yeah. All right, so we went from exponential growth to logistic growth, and this is all fine, but it doesn't describe any spatial variations. So now you're in chapter 2 of your textbook, and we have to go to something that can involve a spatial component. And sort of the thing that everybody does, and it's kind of the most natural, is now to incorporate something that's going to allow expansion of the tumor. And so that's a diffusion term right here, right? So we now have partial derivative of n with respect to time, and a partial derivative of n with respect to the 3 spatial dimensions. And so if I have 1 derivative in time and 2 derivatives in space, which is what I got right here, then that's a diffusion equation. So it's going to describe how it's diffusing out. And there's our proliferation term right here. So the parameters we care about are this theta and this K and this D. Those are the things that are going to be driving how the system, how the tumor grows, proliferates, and how it invades the surrounding tissue. And then we have to somehow get our hands on what these N is. And we've already met one way that can do that for us, and it's that diffusion-weighted MRI that we can use to estimate cell density that we can use as estimates into this N here. So this is a repeat of what's on the previous slide, just to keep the conversation going. And then, in our early days, we took this model right here, or a lot of people did, and it calibrated it to tumors over time, and then projected forward in time to see how the prediction would go. Calibrate the model first, predict it forward in time. And by calibrate, I mean I have multiple data points, multiple imaging time points, and I take this model and I fit it to that data and calibrate it so that the D, the K, and or the theta are make the model maximally match the data. So the calibration fixes the unknown parameters, and then you can run it forward in time And when we did this, our tumors were much larger than the tumors that we were seeing, like in the mouse or rat or in the human. And that's, of course, when it occurred to us, because hindsight's 2020, or I just wasn't smart enough, most tumors don't just expand in a radially symmetric manner, right? So we had to couple the diffusion of tumor cells to the mechanical properties of the surrounding tissue, right? Because these tumors aren't just growing out into space, there's tissue around them and they have mechanical forces, so you can't just assume isotropic diffusion, right? We had to get past this term right here. So what we did, this right here, is just our reaction diffusion equation. It's just this repeat right here. And then we took this tumor cell diffusion and coupled it or damped it exponentially by something called the von Mises stress right here. So you have, this is our equilibrium equation right here. The divergence of the Cauchy stress tensor is proportional to the change in cell number. And so we can solve this differential equation because we're getting our n estimate from our diffusion data. We can solve this for sigma. And then we compute the von Mises stress, which you just get from the diagonal elements after you diagonalize the Cauchy stress tensor. So then that just becomes a number that you can put in there. And basically what it means is the cells are not going to migrate in the direction of the highest stresses. They're going to be like everything else in the known universe and go for the path of least resistance. And that's what this says. Describes how tumor cell diffusion is damped by coupling it to tissue stiffness. And so that's what happened. The last step in our math model here is to add a treatment term. So this business right here, the rate of change of n at position x and t with respect to time is equal to our diffusion term plus our proliferation, our logistic proliferation. And remember that d is coupled to the mechanics from that equation on the previous slide. And this is the new term right here. We got to kill these tumor cells somehow. So they're being removed, that's this negative right here, in a way that's proportional to the efficacy of the drug, called alpha sub n, and is the nth drug. What its initial concentration is, which we're going to get from our contrast-enhanced MRI data, and then its efficacy is waning due to either some version of it being eliminated from the system. So these tumor cells are going to be stripped off based on the efficacy of the nth drug. That the efficacy is also waning due to elimination from the body, and you have some initial concentration at time zero due to your that you get from your estimate of the contrast-enhanced MRI data. So in words, this is movement of the tumor cells, this is the proliferation of tumor cells, and this is the treatment of the tumor cells. This is probably a good time to say, are there any questions or comments?
When we say it's the nth drug, so is this assuming we're going to use multiple drugs to treat?
Yeah, that's exactly right. Most cancer patients do not receive just one drug. They receive multiple, and sometimes they're sequential and sometimes they're simultaneous, right? So this is just written out generally for the nth drug, meaning that you could have 1, 2, 3, et cetera, number of drugs. In practice, we typically don't have enough data to separate the effects of all of these drugs out, to even if there's just 2. So we drop this summation, and this alpha just becomes the efficacy of the treatment rather than an individual drug. At least that's what has to happen for the in vivo case. Unless the drugs are separated far in time, then you usually can, or then you can at least estimate them separately because you have a time course at which they're washing out of the body that you get from phase 1 clinical trials. Did that answer the question?
Yes, thank you.
Oh, okay, cool, great. Other questions or comments?
Okay, cool, great.
All right. So this is our PDE that we're going to use to calibrate to our system. And so here's an example of how this can go. So you have your measurements of your tumor cellularity in space and in time. So these are 3 different time points. Same patient being imaged at 3 different time points. And the idea is, you're going to take these two of them to calibrate to your model and then predict to the third. So I'm going to push go here in a moment, and this row here is going to slide over here. And the idea is, how does your prediction match what's being observed down here? What's being observed down here. And then up here on top is our estimate of drug delivery. So our estimate of drug delivery comes from the contrast-enhanced MRI stuff that's gotten right here. The first 2 time points are used to calibrate the unknown parameters. For us, it's mostly this K of X, the proliferation map, and then one global alpha drug, a global parameter for drug efficacy. Now, there are lots of ways to attack this because in principle, you have multiple parameters here. You have this D, this diffusion term. You have K, which we know is important to estimate at a voxel level location, or at least on some grid across the tumor, because this is such a heterogeneous parameter across the tumor. There is the carrying capacity, the number of cells you can maximally be supported in the pixel of interest. Then there is the efficacy, so there's the degree that it wanes. So a priori, there's 1, 2, 3, a field, and perhaps this fourth parameter right here. So that on its own, we can't do. We don't typically have enough data to do this. In some disease settings, we can do this because we have many time points to calibrate the model, but in many, we don't. So this is what we do. We've done, depending on the disease type, you do a sensitivity analysis, you figure out which parameters are important, right? So as it turns out, in breast tumors, they very rarely expand. So D, we can fix at some nominal value that we get from a population average, right? So that limits the difficulty there. This beta, the rate at which the efficacy is waning, you can get this estimate from phase 1 clinical trials where they look at the pharmacokinetics to see how drugs are removed from the body. Every patient who goes on a phase 1 trial will have blood drawn periodically after the injection of the treatment, and they'll see how much drug is left in the system, and they see how it's washing out. So we can get an estimate on beta, and we typically have a median value for that plus a range, which is going to factor into our error bars for our prediction. And so what that leaves us with is really, the theta right here. This is the carrying capacity. That's the maximum number of cells you can fit in a voxel. So we know the voxel dimensions because we acquired the images. So it's typically on the order of a cubic millimeter, and you make then an estimate of a tumor cell size. Oblate spheroids of a diameter of about 12 microns. And then assuming a packing fraction of whatever, it's like 0.72, mathematicians long ago cared a lot about packing fractions, different size objects in different size containers. So you can get a decent estimate of how many cells can physically fit in a voxel. So what that leaves you with at the end of the day for really caring about is this K of X field and this global alpha efficacy thing. And that's what our that's what our sensitivity analysis tells us are the most important things to go after. So those are the things we go after and try to calibrate using these first 2 time points, which we then run forward in time like this. So every time there's a boom right here, that's when the drug is being delivered. It has a corresponding effect on this on the tumor right here. And the idea is, how does our prediction match with what's observed? So let's look at that again. I'm going to hit play here. This is how the tumor cell density is changing based on the drug that's being delivered here via this model. And you want to be able to calibrate it well and then predict well. So this is what kind of happens going forward. Every time there's an arrow, that's another hit of drug, and it has a corresponding effect on the cell density right here. And then we want to predict, match the prediction to what is observed. And so here, so there's a lot more details discussed there. That's hopefully a teaser. So I was hoping to take a pause right here for just a couple of minutes to get people stretch their legs, and I'm going to take a drink of water, and then we'll come back and dive into the details more about how this is done. Is that agreeable to people, or are people in a time crunch and want to get through the material?
I just have a quick question before we move on.
Okay.
So you have these arrows where the drug's being administered. Is this like an intermittent treatment schedule, or is this just sort of, the idea of the patient comes in for the drug at this time and we give it to them as standard procedure?
I'm not sure how your 2 examples were different. This is exactly what.
Is it a chemotherapy-based drug?
Yeah, so this is a systemic therapy. So this is real data. This is not simulated stuff. This is a real patient that came in and received, in this case, 4 cycles of this chemotherapy. And although the time is not indicated on here, this is what happens. They come in at these regular intervals, and so we use typically the first 2 to calibrate the model, and then once the parameters are known, we then run it forward in time to predict. So usually not usually, you pretty much always know when they're really structured. The timing of these things are really structured. So you know when the drug is being delivered, which means you can say what its maximum value is, and then when it's washing out, what rate it's washing out at, and what time course that's over. So you have a bit of information there. Yeah.
Okay, thanks.
Okay. All right. Are we okay? Did you guys want to take a break, or do you want to continue going?
No, a small break is fine.
Okay, we'll take a 2-minute break. I'm going to drink some water, and I'll be right back. All right, friends, you ready for the last 15 or 20 minutes here? Of course, you get me again on Thursday, so it never ends. All right. Okay. So now we're going to dive into more of the details on linking this patient-specific imaging data to mathematical modeling. Our introduction to mathematical modeling, at least one flavor that you can use to link to the imaging data. And remember, the imaging data, anatomical stuff tells us about the computational domain, how we can segment it, how it needs to be registered, which we're going to talk about next. And then the more functional things tell us about the parameters, about the measurements we can actually incorporate into the model. So things like blood flow and vessel permeability and cell density, and then glucose metabolism and cell receptors and so forth. So here's how this actually plays out. There's a whole bunch of pre-processing that has to happen, although most of it is automated nowadays. This is the data that we acquire. These are the two types that we've zeroed in on for today, the diffusion-weighted MRI and the contrast-enhanced MRI. You collect them with different types of what are called a diffusion weighting, and so that lets you compute the apparent diffusion coefficient map. And then here's the pre-contrast image, and then here's the post-contrast images. And if you squint, you can convince yourself that these guys are much brighter than the ones over here. So as the contrast agent comes in, it causes the tumor to enhance. There's the pre-processing. We have to do the registration. We have to align these images over time, both within one image set, because you want your estimate of cell density to be lined up with your estimate of blood flow, because that's going to tell you how the drug gets delivered to those cells. So you have to do intra-visit registration, and the images are not always acquired with the same field of view. So you have to align these things over the course of a single image, but then you also have to do it over time because patients come back. Because all these images all these models are dynamic, so they have to have some sort of separation in time so you can calibrate and capture those dynamics, right? So then you do the pre-processing to do to align the images, and then there's the inter-visit registration. This is actually not trivial. We use a tumor-constrained and non-rigid registration. What it means is the tumor itself is minimally deformed, and all the surrounding tissue can be deformed maximally. So you look at these deformation fields, and you try to do it so that the area around the tumor is not deformed, but all the other stuff can be deformed. At the end of the day, you want these tumor to be well aligned without having morphed or reduced or enlarged the shape of the tumor, right? Because you want the changes that you see in the tumor to be present still after the registration, right? You don't want to influence the biology through your registration. So after they've been registered at both within one visit and then between the visits, then you can segment the tissue, use your high-resolution images to segment here into fibroglandular tissue. The yellow stuff, the teal stuff is the adipose tissue, and the tumor right here is the red. Here it is for visit 1 and visit 2, and they're aligned, and then you can see the cell density map. The red indicates a higher cell density, the blues and yellows, blues and greens are less. And so these are the cell density maps. So those are the things that are going into that N of X comma T in our tumor model from the previous slide. And so this bit right here, wherever there's an N, that is populated from these guys. And of course, this is in 3 dimensions. This is just one slice, but you have a slice of this throughout the whole, in this case, the whole breast or whatever you happen to be imaging. The contrast enhanced stuff tells you the estimate of this, and then we talked about how you use those data to calibrate the K of X and the alpha sub N are really the key drivers for us. So this is a repeat movement, proliferation, treatment, and here's our video again. We had to do all the pre-processing on the previous slide to actually make this thing fly, but then you have it, you can run it forward, and you can have your spatially resolved drug kinetics, inflicting the influence on the cell density. So you do this for a bunch of patients, right? So here is one surface of a woman with a breast tumor right here. The blue is the predicted and the red is the observed, and you can see that it actually does a pretty good job of matching the size and shape of it at the end of therapy there. And then here's the measured cell counts versus the predicted over 139 patients, and you can see that there's actually a really good match between the measured and the predicted. Same for the volume change. Sorry, for just the volume right here. With really high concordance correlation coefficients. If you're not familiar with the CCC, it's like a Pearson correlation coefficient, only there's a penalty if you're off the line of unity. So it's a pretty conservative estimate of comparing 2 different things. And
so Tom, I have a question. Since you are solving a diffusion equation, you will have level sets, right? So how do you delineate your predicted tumor size?
Right. So what we have done is at the end of the day, or at the end of your simulation, you have a prediction for cell number across the whole domain. And the question is what do you say as is tumor and what is not tumor? And so by trial and error, this is one of those unsettling things. Just looking at lots of different disease sites and lots of different patient data, we call a pixel a tumor if we predict that more than 10% of it will have tumor cells in it.
I see.
So that's that's just an arbitrary threshold that seems to match the data really well and leads to good predictions, but it's not like it's handed down from on high, right? It's a bit unsettling.
Yeah, and I know Christine Swanson has used 16%, so it's kind of in the ballpark.
Yeah, that comes from. So she, if memory serves, and people should check me on this, she is looking at T1 and T2 weighted MRI data, and people have done things where they will, in the case of brain tumors, which I think historically is what she's studied the most, on a biopsy specimens or surgical specimens, they will look at how the cell density falls off from the center of the tumor to the end, and then look at that, how that compares to T2 weighted MR images, and see at which point the T2 weighted MR says that there's no more tumor cells left, and then look at how that corresponds to the surgical specimen and that 16%. I think that's where that comes from, but someone should check that.
Yeah. Okay. Thanks.
Yeah. But honestly, we have to do a better job of dotting that I and crossing that T. Yeah. So when you use this to make your prediction, you're getting an area in the curve of 0.89. And I'm glad there were early questions about that number, because this 0.89 is basically the same as that 0.88 that we got from combining just the diffusion and the contrast enhanced stuff for separating patients. But there's a couple of key things here that are not that subtle, but they may seem subtle. So that 0.88 we got from combining the diffusion and the contrast enhanced MRI stuff, that is a retrospective statistical separation of groups of patients. Here, this is prospective. One patient, you're using their data to calibrate the model to make one prediction. There's no training data set. There's no population average that's being used here. And so now you're having this accuracy with a patient-specific data. And more importantly, perhaps, you now have, at least in some sense, a mechanism-based model where you have components to it that correspond to movement of the tumor cells, their proliferation, their response to therapy, and that's all connected to the mechanics of the surrounding tissue. So now you have stuff that's readily interpretable and that you can then you can sink your teeth into, so that if you have confidence in its prediction, you can go on the computer and try different therapeutic regimens to see how you can do better or worse than what the patient actually received, and maybe that will guide subsequent clinical trials. We're going to talk about a lot of that on Thursday when we talk about digital twins. So this does a decent job of predicting how these breast tumors are changing in space and time, at least in this pre-surgical neoadjuvant setting. So the question is, does it generalize? So the stuff I'd shown you before was all studies that we were intimately involved with. This is now using publicly available data. This is from the iSpy data, so it's multi-site trial, but it's the same kind of design. You have visit 1 and visit 2. You calibrate to predict forward in time. It's very analogous to what we just finished talking about, but it's from 10 different sites. This is important, of course, because different sites. If you could do things at one site, that's great. But when you can go to multiple sites and come up with the same predictive value, that's really something, because all of those sites have different QA, QC, even though they're all supposed to adhere to the same thing, but there's different people collecting the data, there's different scanners. It's a whole other level of noise. So being able to say that you can hold up to this is good. And so here is sort of the pipeline for the same idea, but in this case right here, the red dots are the observed, and here's our predicted. There's these humps because we have information on when the drug is being delivered, right? And so you can see this is a patient we would predict to have residual disease. In fact, that's what they have here. So there's visit 1, visit 2, visit 3, and then here it is rendered in 3D. You can see in this case, our prediction is actually underestimating what the patient actually had, but still calling it as a non-responder. Then here, this is a patient who's responding, and you can see that their red dots are going down nicely, and this is a correctly predicted non-responder. Then you do the change in observed total tumor cell number versus what's predicted, and you still have this really high CCC in these 91 patients that were collected across 10 different sites. A similar story for the change in tumor volume right here. So these CCCs are still solid with patients from 10 different centers. So we're starting to believe that this stuff actually works. Here it is, similar idea for brain cancer. This is the predicted on the bottom row. It's 1 month post radiation therapy. So we've moved from systemic therapy to radiation therapy. And so you can see some cases we do a really good job. Some cases we underestimate. Some cases we overestimate. But a lot of cases we do a pretty good job. And when you do this plot of measured versus modeled, it's not so bad, although there's clearly a systemic deviation here. So our model is not perfect. Similar results for prostate cancer, just cut to the chase here and showing the measured versus the predicted. For the calibration, both the calibration component and the forecasting component, pretty good. And then just hot off the press, we just started doing this with cervical cancer. So this is like the first, we've done like 2 patients on this. Cervical cancer is really difficult. You're working in the abdomen here. So, the big problem for us here is that the registration over time, so that you can calibrate the model and then check your prediction. Registration in the abdomen is very difficult. As the bladder fills up, it pushes things around. So as food moves through the intestines, things get shifted around. So doing that longitudinal registration is a real difficult point. One more thing, and then we'll call it a day. What about using the PET data? So this. Actually, someone's ringing the doorbell. I don't know who this is. They're doing it repeatedly. It might be my son. I'll be right back in 30 seconds. Okay, sorry about that. But we're all good. No one's hurt. Everything's fine. So this is our last example for the day. This is looking at PET data. This is with those, we talked about targeted PET tracers. This is a very early effort. This is a place where the field could be going. This data had MRI and then a copper 64 labeled trastuzumab. So trastuzumab is a standard of care drug that's used to hit HER2 positive breast cancer. So we're going to use our MRI stuff to estimate, to be able to build the computational domain, segment the tissue types just like we've done before. And then we'll also use the MRI data to tell us about delivery of the systemic cytotoxic therapy, and the MRI data to tell us about cell density through our diffusion MRI stuff. But then this guy is going to tell us where this targeted drug gets, right? Because it's the same as the drug itself, only it's been labeled, and so its distribution is going to be very similar to the naked drug, right? Mm-hmm. So it's a similar idea. You have your here are the data types we get: the diffusion MRI, the contrast MRI, the copper labeled trastuzumab. So these are the things that we're going to use to predict what's going on at surgery. So once the model is parameterized with the MRI and PET data, we can forecast treatment response on an individual patient basis. And I got to stress here, sort of. There's a ton of work to do here. This was a proof of principle thing. These types of data are difficult to get your hands on, and then it's not exactly clear what the best way is to model this now that we have a targeted therapy right here. So this is just a repeat of what's on the previous slide. Right, here's our actual data. So here's the post-contrast MRI. The tumor is inside the box right here on each slide right here. So you have your contrast-enhanced MRI data tell you about delivery of the chemotherapy, the non-targeted drug. You have your apparent diffusion coefficient from the MRI to tell you about cell density, and then you have your copper labeled trastuzumab to tell you about the delivery of the targeted therapy. So it's a similar model as before, but we have to do the same steps as we have to segment the tumor, make our maps of the tumor cells, distribution of the broad spectrum of the HERS targeted there. Then this is the model that we're using right here. Again, a diffusion term, logistic growth, and then there's our therapy term that's broken up into two pieces. One is the chemotherapy, and one it says chemotherapy, but it should not. It's the trastuzumab component right there. All right, and so this is what we're coming up with. This is the MRI-based model prediction. This is what the this is. Yeah, here's the PET MRI base. This is just using the MRI. This is using the PET and the MRI, and you can see that they're different because we're using different data types. And then here's the non-responder right here, and there's more similarity. Although in both cases they are the extent of the disease is less in the PET MRI data. So at surgery, patient 1, that's the left column, response was designated as a pathological complete response. Whereas in patient 2, there was still residual disease over here, and the PET MRI-based model predicts overall small tumors with lower overall cellularity, and that matched with the data, but it was just 2 patients. So this is really next level stuff of where the field can go in trying to combine these targeted therapies with mathematical modeling.
Nice.
All right, so we're going to pick up here tomorrow, estimating drug delivery with imaging and modeling, and then from there, we will go into digital twins, and hopefully it's of interest. And so we'll stop here for the material for today, but are there any questions or comments?
Yeah, first of all, Thomas, thank you very much for this firework of oncology modeling. Really cool. I can't wait to see the second part on Thursday. I have to make my way to the airport now, but I leave the Zoom open, and I invite questions. Yeah, I see students are a bit hesitant. So Tom, let me ask you a question. I worked with computer scientists here as well, and all these registration, data manipulation, and then you get imaging data where the scales of the grayscales is different. You need to adjust for this, and as you said, you have movement on the tissue. You need to adjust for this. I mean, this must be huge amount of work.
It is a huge amount of work. It's kind of fortunate for our team because my degree back in the day was in medical imaging, and so we did a lot of this stuff just as part of our daily routine. So
okay.
we had a knowledge base on this, and actually, how this all started was I was at the beach about 12 years ago, and I was reading this review, a historical review of meteorology, just because I always liked weather modeling. And there was one paragraph in there that talked about 100 years ago, there was no physics and or measurements, and weather modeling was all just guesswork and experience of the investigator. And I thought, we could swap out meteorology here and put in oncology here. And so then we started to steal a bunch of ideas of the philosophy, the way these problems are framed from meteorology and applied to oncology. And we were lucky that we had been working with imaging data. So when I got back, we went to the whiteboard and we made a list of every measurement we thought we could make with imaging. And then we tried to start building models that we could make use of those data.
Yeah.
So a lot of that's, but it does help to have somebody on your team who's familiar with it. Yeah.
For sure. Nice. Are there any other questions?
Well, if anybody, wait, there's something here in the chat. Is this? Well, here. If anybody has any question, feel free to shoot me a note, and I hope you come back on Thursday.